All right, so we know that we can take an acid chloride or a carboxylic acid, which is an acid derivative, and we can treat it with thionyl chloride, SOCl2. We didn't show that mechanism, and we won't, but we can make the acid chloride. One thing I said we can do is we can do things like make other acid derivatives, such as in this case, this is an ester. So how do we do this? You can treat this with an alkoxide. Typically the solvent here will be the alcohol, the conjugate acid of our alkoxide. So how does this work? Let's talk about the mechanism for this reaction. So we have our acid chloride, and we're going to treat it with our alkoxide. You know, this R group, it could be really almost anything. It doesn't have to be small and simple like methyl or ethyl. It could be cyclohexyls or even bigger. So this is a nucleophile. This is an electrophile at the carbonyl. And so we've seen this over and over again. Decent nucleophiles will attack a carbonyl, and that always leads to a tetrahedral intermediate. Now, once we get a tetrahedral intermediate, we got a glimpse of this in the last video, but once we get to acid derivatives, the answer isn't we'll protonate our tetrahedral intermediate. The tetrahedral intermediate actually it loses a leaving group, and that's one of the key roles of putting this chlorine on the tetrahedral intermediate. This O- can swing back down, reform the carbonyl, something we haven't talked about before. And as that happens, let's finish our mechanism. We're going to kick out the chloride. And so what's left on our carbonyl is just our new OR group. And we've lost chloride. And that chloride is not lonely because it has sodium to keep it company. So and then, we're going to wash this just away in the reaction. But here is our ester product. Now, why haven't we talked about this reaction in the middle, this collapsing of the tetrahedral intermediate to kick out a leaving group? Well, we haven't talked about it because this is the first time we've had a group on that carbon that could potentially leave. Remember, we're talking about acid derivatives, and the whole point of the acid derivatives is we have a third bond to our an electronegative atom from carbon. So before this carbon in the middle, and here at the tetrahedral intermediate, we only had groups that weren't very good leaving groups, but now we have a good leaving group, the chloride. This is a really simple reaction. It works well. Actually, you will see variations of this where instead of using an alkoxide, and let's go back on that. There we go. Instead of using an alkoxide, people will just use an alcohol with a little bit of a weak base. I'm not going to specify a base. It's some weak base. Sure I will. Pyridine. That works. And what this does, it does the same thing. Actually, the neutral alcohol is nucleophilic enough, even though it's a weak nucleophile, to attack our carbonyl. It changes the mechanism a bit, but you get the same thing. When I show these in class, I will always go with the more strongly nucleophilic alkoxide, but it's not universally required. Regardless, the point is, under either these more basic conditions or less basic conditions, we can do what's considered a nucleophilic substitution on our carbonyl. And in doing so, we're substituting out the chloride and replacing it with an OR group to make, in the end, an ester.